Okay, now we're going to start off with benzene. Now, hopefully you remember that benzene is a resonance structure with alternating double bonds. You can also represent benzene most commonly with this circle representing that resonance structure. Now, there is evidence for the resonance structure. Most importantly is bond length. I should say evidence for resonance, okay, is bond length. All of the bond lengths are the same, as opposed to the single bonds being longer than the double, which would be, if it was not a resonance structure, you would have a single bond which would be longer and weaker than a double bond, which would be shorter and stronger. Okay. We find that there are only 3 isomers that occur, okay, which would not be the case if it was actually a blend of these two resonance structure, or if it was this one and this one as opposed to a blending of these two, which would be the resonance structure. Okay. The other evidence for resonance structure is if I have a benzene molecule and I react it with chlorine in the presence of aluminum chloride, I end up substituting on the ring. Instead of breaking that double bond, which, if it was more of an alkene, it would be a breaking of the bond in an addition reaction as opposed to a substitution. Okay, so further evidence is a substitution reaction occurs. Instead of an addition reaction. Okay. The other thing that we need to know is the mechanism for the nitration of benzene. Oh. So the first step in this mechanism is the reaction of the nitric acid and sulfuric acid. So the nitration of benzene occurs in a concentrated acidic solution, actually under reflux. What happens here is we form the electrophile NO2+, and then we have water and 2 hydrogen sulfate ions. Okay, so the second part of this structure, or I'm sorry, this mechanism, is this electrophile. The electrons, okay, and you have to start the electrons or the curly arrow from the circle representing the electron pair and ending at the nucleophile NO2. Okay, so then we draw the intermediate, which would have the H and the NO2. Okay. Oh, I did something wrong. Okay. Your circle representing the resonance structure has now been broken because that electron pair has come out and made this bond with the O2, of the NO2 plus. This hydrogen, remember, this really was already there, so we're just adding this NO2 at that same spot. The next part of your mechanism is going to be where that intermediate, have the intermediate, make sure that that half circle goes and makes it around 5 of those carbons. Now for the second part, this bond from the hydrogen is going to go back into the structure, so the curly arrow has to start at the bond of the hydrogen, and then I'm going to go back in and make that NNO2. Okay, so you need to know that mechanism, and there are things that are definitely looked for within this mechanism. One is that the first curly arrow starts at there, ends at the electrophile. It looks for this circle to go around 5 carbons with the plus sign, and then we're going to go from that bond, oh, I don't know what I did there, from that bond back into the circle. Those are the things that are looked for. Let's move on to reduction reactions. Here we don't need to know any mechanisms, but we do need to know that we're going to take aldehydes back to primary alcohols. And remember, we have gone over the reactions going from a primary alcohol to an aldehyde. If you remember the acidified dichromate solution under distillation. Okay, and then we can also take ketones and reduce them back to secondary alcohols. And this is going to be by using a sodium borohydride as the reducing agent in methanol. Okay, so all you need to know here really is the reaction conditions to do this. Now, if you remember, to go from a primary alcohol to a carboxylic, we needed to have an acidified dichromate solution and reflux. So to reduce a carboxylic acid to the primary alcohol, we need a stronger, I keep adding an E, we need a stronger reducing agent, and that is going to be the lithium aluminum hydride in a dry ethanol. I've also seen it written as ether. Okay, and that's the first part. The second part is just an acidic environment. The reasons why you would not necessarily want to just use this stronger reducing agent is because it is more complex. Okay, so this is a stronger reducing agent, but it is more difficult to use. So this agent will also reduce the aldehyde and the ketone, but but the sodium borohydrate will not reduce the carboxylic. It will reduce the aldehyde and the ketone. And then the last thing is going to be the reaction of nitrobenzene. We have nitrobenzene. I'm sorry, it's the reduction. Goodness me. Reduction of nitrobenzene. Okay, and this is going to be using tin and concentrated hydrochloric. It first goes to make NH3 on a benzene plus 2 waters and a hydroxyl, and then this will further react to form NH2 and water.